So this is the last part of my demonstration, and in this section, I'm going to focus on using the Garch model to forecast volatility, and we'll do that primarily using this equation here. So this will be the expected variance in a future time period, and it's equal to the long-term variance plus the alpha and beta raised to the power of whatever the time period is, which I'll show you in a second, and then multiplied by the present variance minus the long-term variance. So before I get started, there are a few pointers. So first of all, part of this table is already populated, and in this case, this variance and return value come from the main data set from December 1st, 2015, I want to say. And those are the starting points, okay? And based on those, I was able to calculate the Garch variance. So I just basically copied, or rather followed, this model, as you can see. So B2 would obviously be equal to omega. B3 would be alpha. The squared return from the previous period is highlighted here as C21 squared. Multiply them twice, and then plus beta multiplied by the variance from the future time period. So I apologize, I mixed up the return earlier. The return is here, okay, C21, and then you can see it's squared. And this is the variance multiplied by beta, but I am following this model. So with that out of the way, that's how we got this value here, and we applied the square root to this value to get the volatility. And I realized that the square root of variance is the standard deviation. That's common knowledge. I've been using the term volatility simply because that's often what's called for in the literature, okay? But it is the same concept as standard deviation. So I mentioned earlier that we would manipulate this formula for expected variance in future time periods. Now, this expected variance is an adaptation of this equation, okay? So it's an algebraic adaptation of this equation, and paying close attention to these values in particular, together the alpha and beta add up to be the persistent factor. So often in time series data, you'll find the volatilities mean revert, or they fall back to the long-term variance. And the greater these two values, the less readily that will happen. In other words, it's more likely to stick with its present variance instead of reverting back to its long-term variance. So it's another important point. So we're going to rather not manipulate, but rather apply this formula to generate the variance inputs and then the volatility inputs. Step, as you can see, is for long-term variance. So long-term variance is up here. I want it to be a reference cell for when I use the formula repeatedly to populate the other cells. So I hit the F4 key plus alpha plus beta and in this case k is equal to 1. It's the first period, and then I'm going to multiply Wow, made a hash of that. So going to multiply by the difference between the variance in the present period and the long-term variance. So because we're predicting for the future and I'm generating a variance for the future, I'm actually going to go back and use this variance here. So it's the variance in B22. It's the variance in the previous time slot. And then I'm going to subtract the long-term variance again. And just for, I guess, safety's purposes, whilst I don't actually want to F4 key that, so I won't. I want to make sure. Okay, so actually I do want to have that as a reference cell. I do want to have this as a reference cell. I don't want to have this as a reference cell because I want to use the variances as they are generated. So I hit the wrong key accidentally. That's fine. So I know that that's beta. And then again, minus the long term. Again, I want this to be a reference cell. So I'm hopeful that this should give the correct value, and it does. Wonderful. So then now I can just scroll down and use this value. So notice, first of all, something very interesting here. The long-term variance is 0.18351%. And as you go through the projected time series, it projects that it will actually mean revert. It'll actually go back to the long-term variance value, okay? And you can see actually the long-term variance value is essentially present for the last 3 time series. So that's what the projection is. For our intents and purposes, I'm also going to show the volatility, okay? And so what we should see from this graph is the volatility essentially evening out. That's what the prediction is. So I'm going to go to insert, going to go to chart, going to choose just a regular 2D line chart. Going to right click within the chart area, going to select data. And so I'm going to add, and the series name will be volatility. And I'm going to highlight. And there we are. So I'm comfortable with the horizontal X labels simply because these are hypothetical time periods, okay? So here we are. So this is the percentage volatility, or I'm sorry, this is the volatility. Not sure whether I changed it to percentage. Hold on. No, I did not. Okay. So I'm actually going to go ahead. I'm sure this is tedious. So that was actually quite a tedious process, but I managed to present the volatility in terms of percentage. And as you can see, I actually went all the way to 4 decimal points to see if I could kind of wring out any differences. But you can see that it reverts pretty sharply. It reverts pretty sharply to a long-term value. In fact, the last 3 time periods are the same. The last 4 time periods are essentially the same, actually. So the reasoning behind this, I imagine, would be because the alpha and beta, the persistent factor, is actually quite small. It's under under 25%. So I imagine that's quite small. Hence, a reversion to the long-term volatility very quickly in this particular setup. So as you can see, if we change the parameters even a little bit, so I'm going to change this randomly to 50. Um, okay, just to see how that would work. And yes, it makes a significant difference because all of a sudden, as I increase the persistence, the slope doesn't flow so sharply to a long-term average, as you can see. So the parameters that you use to forecast the volatility are also important, and we've been through pretty vigorous methodology on how to do that in previous lectures. Thank you very much for your time. Take care.